lecture is going to be a little bit more technical about computer science and alignment, AI alignment. He's also the head of the, I guess, theory and AI alignment in UT. Yeah. So anyway, if you want to hear a more extensive introduction, look at the recording of yesterday's talk.
Okay. All right. Thanks. I offered several physics-related topics to Zohar that I could speak about, since I know this is the Geometry and Physics Center. Zohar said, no, we want to hear about AI alignment. So I don't know, for some reason people are just interested in whether or not how to prevent the world from being destroyed by AI, which is, I would just as soon talk about quantum complexity classes or whatever. But I have started dabbling in this topic of AI alignment over the last 4 years. And the way, I mean, I almost don't have to justify why. It's like, who isn't dabbling in AI these days? But the way it happened was that some people from OpenAI named Ilya Sutskever and Jan Leike approached me in the spring of 2022. And they said, listen, we're from this little organization called OpenAI. We're just, we're a little nonprofit that's just trying to, get this right for humanity. We're not, and make sure that it's not driven by the profit motive, and that it's done in human interest. We think, AI could be really dangerous, and we think that, making it safe is very, very deeply involves theoretical computer science. And so, we want you to get involved. And I said, why do you want me? I'm a quantum computing theorist. This has nothing to do with quantum computing. I did study AI for my first year of my PhD in Berkeley. That was way back in 2000, way before AI could do anything like what it's doing now. But already then, I could see that like statistical approaches to machine learning, that no one really understood, were just sort of wiping the floor with more logical approaches. But I also saw that it was very hard to prove anything about them, right? Most of the progress was empirical, and that sort of pushed me into quantum computing, where we could prove things. And so I really didn't have any current knowledge of, or much current knowledge of AI. I mean, of course, I had, this was before ChatGPT had come out. I had played around with GPT-3, though. I had been, I had been impressed by it. I knew that this was something new and different, because, I had, and that's sort of the people who were saying, this is just another, Eliza-like, trivial chatbot. This is just a toy. That these people were sort of missing what was happening, because if they had actually tried the sort of previous chatbots and compared to this, they would see there has been a step change in what is possible. And so I was interested. So I took a 1-year leave to go work at OpenAI, right? And they said, the reason, why did they find me? Basically just because they were fans of my blog. Okay, so whatever. Also actually, Paul Christiano, who was sort of, who had earlier sort of led a safety research at OpenAI, who then became founder of the Alignment Research Center, so really a leader in this whole area, and bringing theoretical computer science into this area, convincing all of them. He had started as an undergrad with me at MIT, right, 15 years ago. And then, he was going to, set to be a superstar of quantum computing. And then, he did this crazy seeming thing a decade ago of leaving to join this, open AI, whatever that was, and do, AI alignment research, whatever that was. So that's so that was some of what brought me into this. So I did a year leave at OpenAI, mostly remotely, which then turned into 2 years. These were 2 years where I got to sort of be a witness, I guess, to some massive events that happened at OpenAI. The release of ChatGPT, the attempt to, by Ilya and others to fire Sam Altman, which then backfired and led to Ilya, and actually almost everyone else who I knew in the safety group at OpenAI leaving or getting pushed out. And then the whole team that I was hired into, the super alignment team, was disbanded by the end of my time there. So then I went back to academia, and now at UT Austin, in addition to the Quantum Information Center, I am running a theory and AI alignment group. We just started a year ago, and part of our goal is to be a consulting shop for anyone doing AI alignment research who has basically a math problem, a theory problem. We hope that they'll come to us, and we'll see what we can do. And that's going to be sort of the subject of this talk. Okay, so there's obviously been tremendous progress in AI over the past 5 years. There has also been progress, I would say, in AI alignment. Okay, we understand more about how to get AIs to sort of follow a given set of values or goals, or at least appear to do so. There's a whole bunch of techniques that many of you have probably heard of. One of them is just a reinforcement learning from human feedback, what's called RLHF. Okay, so after you train your base model, which is your basic giant neural net that's been optimized for predicting the next token, just predicting what word comes next, then that in some sense you have something with a lot of intelligence, but which is not really directed toward much that humans would find useful, right? And so then you have to sort of point it in a direction. Okay, and this was back, by the way, one of the main things that Paul Christiano pioneered, which you could call it safety, but ironically, this was also what allowed ChatGPT and all the rest to be released as consumer products in the first place. Okay, so what you do is you just hire a whole bunch of contractors to look at a whole bunch of outputs and upvote and downvote them and say we want more like this, we want less like that. Okay, and and this works. I would say shockingly well, right? It actually it generalizes from the examples. It understands it's supposed to respond to your question rather than going off on random tangents. You can say okay, this answer where you were helping the user, yes, you were helping the user, but the user was asking you how to build chemical weapons, so actually you shouldn't have been helping the user. It was okay, it understands that, right? So that's one thing that's done. Another thing that's done is just literally writing constitutions. Okay, that you can just literally as a kid, right? I read Asimov and dreamed of okay, we're going to build AIs with the 3 laws of robotics and just instruct them in how to behave. And then I became an actual computer scientist, and I learned that real computer science has nothing whatsoever to do with that. It's just not like that at all. You don't just tell these things in English and now here we are 30 years later, and it is like that. Okay, sometimes people are just literally writing in English, sets of moral instructions that they want AIs to follow, including which ones override which other ones. Okay, much like in Asimov's stories. Okay, of course, if you read Asimov's stories, they're all about all the situations where this didn't work. Okay, so that might give us a little bit of pause. But Anthropic, for example, has moral philosophers on staff. Okay, and they have what's called the soul document. Okay, it's basically like Aristotelian virtue ethics. Okay, they have like a 30,000 word document just sort of explaining, not what Claude is supposed to do in particular situations, but what values it is supposed to exemplify, right? And so now and one thing we've learned is that models actually like they can actually follow explicit instructions about what values they should have, even when with hindsight we didn't want that. Right, so there was the famous case where Gemini was told to prioritize diversity and inclusion in all of it, the images that it generated, and so it started generating diverse Nazis, right? Or it would make the American founding fathers diverse, right? And people had a lot of fun making fun of that. That's maybe less bad than what happened with Grok, which is Elon Musk's AI, where he's apparently Musk personally said we have to tell it to be less woke. Tell it to be less woke, less woke. And so then at some point it said, okay, I am Mecha Hitler, it was, you can't accuse it of not following the instruction, right? So, and then I guess they backtracked a little bit and they said, okay, I guess be just a little bit woke, right? So, okay, but the point I wanted to make is that all these kinds of techniques that people have been exploring, these are going to be, I think, tremendously important in shaping, what I would regard as, maybe the most consequential technology that humans are ever going to be building. And so, yes, it's extremely important to try to get this right. I'm glad that there are people, thinking about how to do this in a sort of pro-human way, in a way that's sort of I would say reflects some humility about the magnitude of what is being created right now. This is not just another consumer product. This is kind of like if orangutans were to create, Homo sapiens, and say, okay, but it's, this is going to go really great because we're just going to make sure that the Homo sapiens stay aligned with orangutan values, whatever they do, right? I mean, that might, you could imagine that going well, but by default, it probably doesn't go so well for the orangutans, right? I think that's kind of the situation that we're in now. That doesn't mean that we're doomed. I don't have confidence in any particular scenario. I think that there's an enormous variance right now, but absolutely we should be thinking about this. Okay, now where I personally had a problem is that all of these kinds of techniques, like they felt more like biology than like math. It felt like we're sort of growing this new entity, and we can sometimes poke it with a stick and see what happens. Right, like when we RL it to be more woke or less woke, here is what happens, and you can write papers about that, but the papers don't have theorems in them, right? They have a lot of maybe they have something that looks like math, but then ultimately you just have to run the eval. You have to run it, and and then you show some bar charts of what happened, and that and that's just not where I have any comparative advantage. So, even if this is mostly like biology, I'm interested in picking off whatever parts of the alignment problem look like math, and trying to make some progress on those. Okay. By the way, I can say something about having worked for 25 years in quantum computing. Say something about the difference. So in quantum computing, I feel like every conversation that I've had with outsiders for decades has been, look, I'm sorry, quantum computers just will not do the thing that that you think they can do. They don't just speed up everything. As any of you heard, if you came to my talk yesterday, right? They give exponential speed ups for certain very, very specific problems, probably not your problem. If you give me an hour, I can explain why in enormous detail, right? And with AI, I feel like my conversations are just the opposite, okay? I say, yes, AI will probably change everything that you care about beyond recognition, and it will do it very soon, but I can't explain why, okay? So, okay, but let's at least see what we can do. Are there pieces of this that can be reduced to math? So I want to just give you little vignettes about sort of 3 different topics that I and my students have thought about. And that we're continuing to think about. So this is sort of both from my work at OpenAI and then from continuing at UT. So the first thing is watermarking. So in the summer of 2022, this was before ChatGPT was out, but GPT-4 already existed. I was able to use it internally as a new OpenAI employee. And I had this, it suddenly hit me. Like every student in the world is going to want to use this to do their homework for them. Okay, and like I'm not that good at seeing the future, right? Like I had friends who were freaking out about AI 15 years ago, right? I was not. Okay, so I don't really see the future that well. But in this case, okay, I did see 6 months into the future, right? And I said, there's going to be enormous demand for some kind of tool that can tell which text came from LLMs and which did not. And how do we solve that? Okay, so it seemed like if we could have a way to just tell which text came from an AI model, that would have a huge range of safety applications, right? It would make it harder to use LLMs, not only for academic cheating, something I'm sure that no one in this room has ever been tempted to do, but when one hears that others have done such things, but also the use of LLMs for political propaganda, for scams, for phishing attacks. Okay, we could try to tamp down on all of this. So how can we detect AI text, right? So the simplest approach is ones that probably many of you have had firsthand experience with, is you just kind of look at it. See, like, are there a whole bunch of M dashes? A whole bunch of, it's not this, it's that, right? A whole bunch of, the word delve, or apparently these days the word goblin, was showing up a lot. Okay, so there are certain tells. Some of them harder to articulate of AI writing, but as the models improve, that's going to get harder and harder to do. I think that's the truth of it, and maybe some of you have already experienced this, right? And so so then you think of other things like we could tell the AI companies, or somehow get them to store everything they generate in some giant database. And then we could let, professors make queries. Did you ever generate this? Did you ever generate that? Okay, there's some obvious privacy concerns there, right? I don't think the AI companies actually want to do that. They would be very scared that if there was some breach, all the private conversations get leaked. Okay, that's possible, but I want to talk about another idea, which is why couldn't we just slightly modify the way that LLMs operate in order to insert a very subtle statistical signal into the choice of words, the choice of tokens, that will let us prove later to high statistical confidence that yes, this document, was generated by this AI model, so that seemed like a natural thing to try. So in 2022, I proposed the first scheme for watermarking LLM outputs. Since then, a bunch of people have built on that and proposed other schemes. But there was a little bit of interesting math here. Okay, so let me tell you a little bit about this. Okay, so the first thing that people said was, well, look, of course you could adjust the probabilities, right? You could insert a watermark by just systematically favoring certain words over others. But if you do that, then people are going to notice that, right? And it's going to decrease the quality of the output. Okay, so clearly there is some inherent trade-off between how much you want to watermark and how much you're degrading the quality of the AI's output. Okay, and so then what I had to explain to people in 2022 was no, actually there's no such trade-off at all. Okay, actually what we should really do here is just use cryptographic pseudo-random functions. Okay, what we ought to be doing is taking the entropy, which is already there in the output of an LLM, just as a byproduct of how it operates, right? And using that to embed our signal. Okay? So just to explain this, you may have seen that when you feed ChatGPT or Claude or whatever the same prompt over and over, you can get a different output each time, right? Now, why is that? Okay, well, it's because how does an LLM work? Well, it just sees the whole universe as a sequence of tokens. Okay, tokens could be words or parts of words, punctuation marks, right? So all the text that it sees is just processed as a sequence of these tokens. Maybe there's 100,000 possible tokens. Let's say that there's K, right? So each of these is we'll think of as integers from 1 up to K. Okay, and then it is a sort of auto-regressive, right? So the question is always, how do we generate the next token? Okay, we're given some tokens, which some of these may be the prompt that was entered by the user, and then the next ones were generated by the LLM itself. Okay, and now we need to generate the next one. Let's say W sub n plus 1. Okay, and what we do, we feed all of these tokens, W1 up to Wn, into a neural net, and then what does that neural net output? It outputs not Wn plus 1 itself, but a probability distribution from which Wn plus 1 is to be sampled. Okay, so the output of our neural net, which happens to be a transformer, which is, a particular architecture, but that's not going to be important for us here. The output is, let's say, a probability distribution D, consisting of K probabilities, P1 up to Pk. Actually, these are logits, so they're things that we exponentiate to get probabilities, but let's just call them probabilities. Okay, and then in a normal operation of the LLM at what's called temperature 1, what we would be doing is just sampling. Just say we just be sampling the next token according to this distribution. Okay, so now I want to do something a little different from that. Okay, so I want to take the entropy, which is there anyway in this distribution, right? And I think typically there might be about 1 bit per token of Shannon entropy, in these distributions. And now, instead of sampling randomly, I want to sample pseudo-randomly. Okay? And not only that, I want to sample pseudo-randomly in a way that encodes a signal that later we can detect. Okay? And crucially, when we go to detect it, we're only going to have the text. Okay? We're not going to have the probability distribution. Okay? So whatever signal we embed has to be there in the tokens. Okay? So how do we do this? So I want to imagine that we have a cryptographic pseudo-random function, because these are just very, very standard tools in modern cryptography. And what I would like is that my pseudo-random function should take as input, our sequence of tokens, as well as a candidate for the next token. Okay, so we're going to take all of these things as input, and then we're going to output a real number. It's technically a floating point, which I'll call r sub I, and which I'll think of as being from 0 to 1, and which sort of is associated with how likely should it be that I set my next token to be I. Okay, so we'll do this for all I from 1 up to k. And now, supposing that I had this, right? Now I would like a deterministic rule for choosing the next token, okay? But which is going to look to a casual user exactly like the next token was chosen from this distribution, okay? But which is actually going to be using these guys favoring the ones with larger r sub i's. Okay, so how do we do that? Right, that's okay. Well, once you've set the problem up in this way, then it's just a calculus homework exercise, right? Which I could give out to some of you guys. I mean, especially this is a physics building. Unlike unlike computer scientists, physicists are good at calculus, right? You could probably, any of you could do this, okay? Turns out that here's what you want to do. You want to choose the token I that maximizes r sub I to the 1 over p sub I power. Okay, so I came up with this rule, just sort of working backwards from what was needed, and then I showed the ML experts at OpenAI, and they told me, this is already known. This is used for other purposes in machine learning, where it's called the Gumbel softmax rule. Okay, so we could call this the Gumbel softmax watermarking scheme. Okay, so and the key property that we get if we do this is that as I would invite you to prove with a little bit of calculus, if r sub I was uniformly random. So if we pretended that these pseudo-random numbers were actually random, then the probability of choosing token I would be exactly p sub I. Okay, this is the key, right? Which then means that if the user was able to tell our watermarked text apart from normal output of our LLM, then in some sense this user would be distinguishing our pseudo-random function from a truly random function, right? They would be breaking our cryptographic primitive. Okay. Now, to be precise, with my original scheme, I don't get true cryptographic indistinguishability, right? For some technical reasons, like if we repeat the same thing over and over, and then you look really carefully, then you can tell it apart. Okay. Later, my former student Sam Gunn and with Miranda Christ and Or Zamir managed to come up with a variant of my scheme where you do get provable, indistinguishability, and that like any user who can tell the output apart from normal LLM output must be able to break the pseudo-random function. Okay. Okay, but now. Yeah. Yeah.
So in order to maximize that, you have to repeat this multiple times?
Well, you have to calculate the r sub I for each I from 1 up to k.
So you generate k pseudo.
Yeah, this is I should say this is an absolutely trivial amount of extra computation on top of the computation that we're already doing for the LLM inference. Okay, so the computation, tax is almost 0. Okay? Yeah.
How long should this text to
Sorry? Oh, yeah, good question. We're going to have to figure that out later, right? So once we construct our scheme, then we can answer the statistical question of how much distinguishing power can we get with how much, from how many tokens. Okay, but to make a long story short, we can get pretty good distinguishing power with a few hundred tokens. Okay, with a few thousand, we can be basically certain. Okay, so so the next question is, how do we detect the watermark? So at detection time, we are given only a sequence of tokens. We don't know what prompt may have led to them, which means we don't know the probabilities. But on the other hand, we can calculate these R sub i's, because R sub i's are a function only of the tokens. Okay? So what we can do is we can compute these real numbers associated to all of the tokens in our sequence, and then we can compute some score. Okay, the score, I wish I could move this, but the score that I recommended to use was just this. Okay, so it's some function that as the R sub i's get closer to 1, that this gets bigger and bigger. Okay. By the way, the intuition here, right, is like the closer p sub I is to 0, the larger is that exponent, which means the more R sub I to the 1 over p sub I is getting suppressed, which means that the less likely that I is to be chosen, which is exactly what we want, right? We want R sub I to have to be really, really big in order for you to choose an I with a low p sub I. Okay, so that makes sense. But now, how do we detect? So let's say that this is our score. I'm going to call this gamma, and what you can prove about this is that this is a random variable, and it has some distribution. Okay, it has a mean and a variance. And if we had just ordinary non-watermarked LLM output, then the mean of this is actually exactly n, and there's some variance. Well, the variance also depends on the average entropy per token. Okay, we'll come back to that. But if text is watermarked, then what we have done is we have systematically biased ourselves toward those tokens I with larger values of R sub I, which means that this gamma will be larger. Okay? C is some constant that will depend on the entropy. Okay, so there's some parameter there, which I'll have to talk about later. Okay, and this also has a mean and a variance. Okay, and then we just get a pretty ordinary looking statistics problem, right? Of how large does n have to be before these two Gaussians have a small enough overlap that we are willing to say to the student, we are almost certain that you cheated. Okay, so we should be clear, that there are sort of type 1 and type 2 errors, right? I'm personally much more worried about falsely accusing a student of cheating, based on the output of the watermark, than I am about missing a student who actually did cheat. Okay, but we would like both of those probabilities to be as small as possible. Yes?
It seems to me that if you change one token or throw out a token or something like that, if your pseudo-random function is something like a hash function, it would completely change the...
Good. Okay, excellent. So what we actually do is we have this function f depend on only, let's say, the last 5 tokens, right? And so this gives you a sort of local robustness property that says as long as, whatever modification you made to the document, as long as it preserves a large fraction of the 5 grams, let's say.
Replace every fifth word with a synonym and
No. So of course, I'm getting to that, right? Of course, there's this whole class of attacks that we will have to worry about. Okay, we can add some. We can try to add some more friction, right? I mean, given like you have thousands and thousands of students, turning in work that has sentences like as a large language model trained by OpenAI and stuff like that. So at least we can catch those students. But yes, there will be a whole set of attacks that we'll have to worry about. Okay, so the basic result that you can prove here is let's define alpha to be the average Shannon entropy per token, conditional on all of the previous tokens as judged by the LLM itself. So I just mean like the average Shannon entropy of these distributions D. Okay? Then if we want to do a classification, watermark versus non-watermark text with error delta, it suffices to have a number of tokens that is like 1 over alpha squared times the log of 1 over delta. Okay, so this is the bound that you get, and so as I said, alpha is typically of order 1. This is fine, right? And so this is actually very favorable, right? And the constants look good too. Okay. Now, why does there have to be this alpha here? Well, like imagine that you asked your LLM list the first 100 prime numbers, right? It can do that, but how on earth would you watermark that, right? Unless you're going to play games with the spacing or the line breaks or something, right? There needs to be entropy, right, in order for you to have any chance of inserting a watermark. Yeah, exactly. Exactly, right. If alpha vanishes, then it makes sense that this diverges. Okay, so I proposed this in 2022. We implemented it. It worked very well. We even tested it out in a limited deployment, and then the decision went to Sam Altman and Mira Murati and the other leadership of OpenAI as to whether to deploy this. They decided not to. There was a whole Wall Street Journal article about why, but basically, there was some survey data saying that some fraction of customers will not like this. And if it is done, they will switch to a competing LLM.
Rely on some like hidden ID assumption?
What? No, it does not. Okay. So, yeah, so it was not deployed. DeepMind actually did deploy something very, very similar to this scheme. You can read their paper about it. It is in what they call synth ID, like this. Okay, but the catch is that you have to apply to DeepMind if you want to be able to detect the watermarks. Okay, and they have been kind of stingy with who they give that out to. Okay, so by the end of the 2 years, I came to feel like probably if people wanted this, a legislative mandate would be needed. So there actually is, yeah.
The function f is public, like.
Yeah, that's so it could be public.
Why do you need to apply it if the function f?
So Google didn't make theirs public.
Oh, okay.
Yeah. But you could imagine making it public. Okay. So yes.
There was a paper a couple of years back talking about non-native speakers.
Mm-hmm. Yeah. Right. So the other argument was, well, what about all the English as a second language speakers who are using GPT to improve the fluency of their prose? Wouldn't it be unfair to them to if everything is watermarked. And I said, well, look, I don't know how to design a watermark that only works on unsympathetic cases. I mean, yes, there are trade-offs here. Then at the same time, I have so many faculty colleagues begging me for this, saying, why have you not deployed this? Right?
Do you have ideas for what might be the solution for not identifying non-native speakers' text as AI generated?
I don't, to be honest. So. Okay, but then of course the other issue is that there are attacks, right? Now so as I said, with this scheme we can get local robustness, meaning if someone changes a few words or reorders some paragraphs, we're still going to see the signal. Okay, that's no problem. Okay, but what about the student who asks ChatGPT to write their term paper for them, but in French? And then they put it into Google Translate, right? Or they say, write my term paper, but insert the word pineapple between each word and the next. Okay, and then the LLM, follows that instruction as it can do, and then you just go and delete all the pineapples, right? And now you have a document that is, with a totally different sequence of n-grams from the one that was watermarked, right? So the watermark's not there. Okay, so I think it is a really fascinating research problem to say, can we watermark at the semantic level? Can we watermark at the level of sort of the underlying concepts, which probably means like the high dimensional vectors that are there inside of the transformer, inside of the neural net, in such a way that effectively one cannot remove the watermark except by rewriting the thing from scratch. I don't even know how to formalize that, but there is some research on that now. I think it's a really interesting thing to know whether it's possible or not. Okay, so I wanted to say a little bit about these two other directions. Okay, just to what? Yes.
Pineapple attack, one by alpha diverges.
Right. So when, yeah, but well, I mean, first of all, I care about the average alpha, right? So the alpha is going to be 0 for pineapple, but it's going to be non-zero for all the interspersed words. Yeah. So you will have, like the document with the pineapples will be correctly watermarked. The issue is just, when someone removes the pineapples.
The alpha, one by alpha diverges. Maybe you cannot fix that.
Yeah, no, it's fine as long as the average alpha is good. Okay, so what is interpretability, right? And to tell the truth, the super alignment people at OpenAI were not that excited about watermarking either, because they said, look, our goal is to make sure that humanity survives, the creation of superintelligence. We are less concerned with students cheating on their homework. Homework will probably just go away anyway, and we don't care. Okay, so. Okay, so there's a huge number of ideas about how do you align a superintelligence. It will be out of my scope to talk about most of them, but one direction that looks particularly promising, that I think a bunch of people from very different points of view can sort of all agree that they like, is interpretability. Okay, so interpretability means sort of, given the weights of the neural net, what can we figure out from them about what is going on inside? And what can we, let's say, we have our neural net. Our neural net is can be characterized by, let's say, a vector of real numbers, which are called weights. Okay, and it takes some inputs, it produces some outputs. Okay, and now so we could imagine just querying a neural net as a black box. Feeding it inputs, getting outputs. And we can learn some things about it that way, but why limit ourselves to that? right? I mean, you know, a huge advantage that we have in trying to control or monitor our AIs is that we have perfect visibility into every single neuron, every single weight, right? We can we have a level of access that neuroscientists only dream of, right? When they're doing stuff in a wet lab, right? So why not exploit that? So now, you know, the theoretical computer science question is going to be, if I give you this vector of weights, what can you figure out in polynomial time? Let's say via an efficient algorithm about what our neural net is doing. Let's say that our neural net, you know, depending on the weight vector W, is some function mapping these input bits to these outputs. So what can we figure out about CW as a function in polynomial time given W? Okay, and so an example of a question that we might ask, all right, I guess I should go over to this board. An example of a question would be, does there exist an input X such that C sub W of X equals the string, you know, interpreting the real numbers as a string in some way, that the output of the neural net is kill all humans, or, you know, initiate the kill all humans protocol, you know, or something like that. Okay, is there any input that causes our neural net to produce? This is just going to be a stand-in for some dangerous output that we want our neural net to not be producing. And so, okay, so now we have a well-defined computational question, you know, that we're asking. The only problem is that this kind of question will essentially always be NP hard, right? Okay, so why? Because we can just encode, you know, neural nets, among all the other things that they are universal computers, right? They are sort of, you know, they can do universal Boolean circuits, which means that we could take any 3-sat, or, you know, pick your favorite NP-complete problem and code it into a neural net, such that by answering this question, you would be solving your favorite NP-complete problem. Okay, so we cannot hope for, in other words, you know, for a general polynomial time algorithm to do this kind of interpretability, you know, unless P equals NP, in which case we're in a different world. Okay, so now I come to, I think, the really, really beautiful idea that Paul Christiano, the founder of Alignment Research Center, who I mentioned before, had a few years ago. Okay, he said, let's just ask whether we can achieve a more limited goal. Okay, so let's just say that I promise you that your neural net satisfies one of two different conditions. Okay, first condition is that we have a random neural net. Okay, what do I mean by a random neural net? I mean that the weights, you know, that define it are just a bunch of independent Gaussian random variables, you know, of mean 0 and variance 1. Okay, this is just a standard model for random neural nets. Okay, and I'll come back to this later, but you know, we will set the parameters in such a way that, like, you know, we will want to set this up so that a random neural net, you know, with high probability would have some input that indeed causes it to kill all humans. Okay, why? Well, because, you know, this C sub W will look like will look pretty much like a random function, right? And as long as the number of, as long as the size of the input space is large compared to the size of the output space, then almost certainly by chance, there will be, yes, some inputs X that cause the unsafe behavior, right? That's what we would expect for the random neural net, okay? But now case 2 is that for some reason our neural net is safe, okay? So in other words, for all X, CW of X is not equal to kill all humans. I'm gonna take that as my stand-in for safe right now. Okay, it never produces this unsafe output. So we might get to case 2 in several ways. Maybe we started in case 1, so we started with random weights, and then we just did gradient descent until we eliminated all of the bad inputs. Okay, or maybe we just kept picking random neural nets until we happened by chance to find one that satisfies this property too. Okay, could be many things. Okay, and now the question that Paul asked is there or is there not a polynomial time algorithm to distinguish case 1 from case 2, given W as input? Right? I think this is a beautiful question. It's really not obvious what the answer should be. Paul, and his ARC organization, they have sort of a whole program of how they think AI alignment should ultimately be solved. That very much depends on the answers to questions like this one being yes. Okay, they want there to, they call it the no coincidence principle. Okay, because basically they want to say when a neural net has some sort of very, very unlikely property that a random neural net would not have, then there should be a short reason for it. Okay, that we can efficiently verify. Okay, so at the very least, if there's not a polynomial time algorithm, they would like there to be an NP witness for case 2, right? They'd like there to be a short proof that you are in case 2 when you are in fact in that case. Okay, what's pretty easy to see is that there is an NP witness that you're in case 1 when you're in case 1, right? What is that witness? Well, it's just the input X that causes the output of kill all humans, right? But the question that they ask, I guess the more general question that they ask is there an NP witness for case 2, right? Their program for alignment depends on their belief, their conjecture that the answer is yes, and that sort of therefore, we will be able to sort of look at neural nets and actually give. It won't just be that they are doing what they do for inscrutable reasons. There will be short proofs that even if they didn't work in the worst case, they would work in the generic case to sort of prove the kinds of behaviors that we want. Yeah.
So I'm a bit confused by why do they want to distinguish safe from random as opposed to safe from random?
Well, okay, because so as I just said, we have no hope of solving this problem in the worst case, in full generality, because it is NP hard. Okay, so so this is sort of a toy model for a thing that might be possible, at least that no one knows how to rule out. Right? When we train, one thing that's worth saying is that when people train neural nets, usually they initialize them to have IID Gaussian weights, right? And then they do gradient descent, on that. And the gradient descent changes it in some way that's incredibly hard to characterize, right? We don't have, a good theoretical model for that, right? It depends a lot on the character of the training data, okay? But we could at least say, okay, the uniformly random, or the Gaussian IID case is something that we can define and study, right? So let's just use this as a toy model. If we can't even do this, then probably, yeah.
Randomly seeing your polynomial time algorithm?
Sure. Yeah, that's totally fine. Yeah. Okay, so I am much more skeptical that the answer is yes here, right? I think that you might have neural nets that have some global property, like never outputting some string, but for a totally obfuscated reason. Okay, that you have no hope of figuring out except by just evaluating the net on like literally every possible input or something like that, right? I don't think there's a short explanation. Yes.
Saying that if you calculated like moments,
Mm-hmm.
the distribution of weights, they all look Gaussian.
Yeah, they are IID Gaussians. That is how the weights were chosen.
Oh, I thought you want to distinguish one from two.
Yeah, that's right. Oh, right. I see. Right. Yeah. So if the moments were different, then it would be easy to distinguish. But yes.
You're saying that it could be that the neural net got moments.
Yes.
Still, it's in
Yes.
non-local property.
Exactly. Good. So yeah, we can, in case 2, it could certainly be that like all the moments that are easy to calculate will look the same, right? Because we're asking about an exponentially unlikely event, right? And and this is the problem, right? So when AI companies deploy their models, like of course they have tested them, right? Of course they've checked them on various inputs, and if the typical output was kill all humans, then okay, then probably that they have to work on that model some more before they release it, right? This is almost literally what happens, right? They don't release models until they look pretty good, in testing. Okay, the fear is that that's not good enough, right? That it might be that the typical behavior looks fine, but then you release it and people are able to find the inputs where the bad behavior nevertheless happens. Okay, so. But what I really like about this question is that between me and Paul Christiano, one of us is right, And unlike with all these questions, so like every week at OpenAI, I would meet with Ilya Sutskever. I would tell him like what progress I'd made on questions like these, watermarking and so on, and he would be like, okay, that's fine, Scott, but what we really wanted you for is what is the mathematical definition of what it means for the AI to love humanity, okay? And every week I'd have to say, Ilya, I'm still thinking about that. I don't have a lot of progress to report on that, okay? What I love about this question is that we could imagine answering it, right? It has an answer. So this year, yeah.
The answer would be yes.
What?
The answer to this would be yes.
Well, okay. So first of all, they have some numerical evidence, right? They tried this out on like random circuits with 10 bits or 20 bits, and what they find is that when you sort of post-select on it being safe, it is typically safe for some really, really trivial, easy to identify reason. Like some particular, the first letter is always set to C, right? So it can't be kill all humans because that had to start with a K, right? It's something stupid like that. And so, they say, well, that should just be the typical case. And I think it's very hard to infer anything from like looking at, circuits on 10 bits. Right? It could be that what happens asymptotically is totally different from that. Okay, so that's where some of the disagreement comes from. So in a paper with an undergrad, actually soon to be my PhD student at UT, named John Dunbar, he and I, we didn't answer Paul's question, but what we did is we at least figured out how to properly ask the question. Okay, in the context of neural nets. Okay, so what is the issue? The issue is when you start thinking about this, there's a question of what do you even mean by a random neural net, right? So, I said, weights are random. I didn't tell you what, but there's another very important thing in a neural net besides the weights, which is the function, right? The activation function that is computed by each neuron. Okay, so, in a neural net, right, we're summing up all these, we're constantly taking these inner products, and then we're feeding the result into some nonlinear function, right? There has to be a nonlinearity. Okay, so standard choices are like the sigmoid, which looks like that, or there's the ReLU, which looks like this. Okay, but there has to be something that induces a nonlinearity. Okay, but now if you're not careful in your choice of activation function, then what you find when you look at these Gaussian random neural nets is that they just converge to nearly a constant function with overwhelming probability, right? And in that case, Paul's question is just not interesting, right? Because like even in case one, the neural net is probably safe. It's probably never outputting kill all humans, right? So the question is like, for which choices of activation function will a random neural net actually give behavior that looks like a random function?
The limit theorem, the first thing you said?
Well, so yeah, I mean, so now we have kind of, a well-defined question in like random neural net theory, and people had studied random neural nets, but somehow not this specific thing, right? And so, but we were able to use techniques from, there's actually a really nice book by physicists called Principles of Deep Learning Theory. It's by Dan Roberts and Sho Yaida and who's the third author? I forget. I have it. Hannon. Okay. And so yeah, so they basically use all kinds of statistical physics techniques to understand neural nets, including random neural nets. And using that, we could give a characterization of for which activation functions, do we get neural nets for which Paul's question makes sense. And basically, so the property that we want is sort of pairwise independence. That like if you evaluate your neural net on two different inputs, x and y, then the outputs look uncorrelated from each other, right? And we can say that this holds at least for shallow neural nets. So let's say we fix the depth of the neural net and then we let the width go to infinity. This holds if and only if, let's call the activation function sigma. Okay, so these are sigma. Okay, this holds if and only if the Gaussian mean of the activation function is 0. Okay. So we need that, like when you take the expectation of sigma over all Gaussian x, that this is 0. So for example, this one is okay, right? The ReLU function is not okay. This one has a positive mean. But if you take sigma x equals ReLU minus 1 over square root of 2 pi, this works. Okay? So there's actually a very simple condition, and now at least we can, because Paul didn't know this, he actually phrased his question in terms of random reversible circuits. There's random circuits of what are called Toffoli gates. Okay, and said, this is because neural nets are kind of too messy. Okay, now we can ask his question, his no coincidence question, in the sort of more relevant context of neural nets. Still doesn't mean we know the answer. We're thinking about it. We have some ideas. But that's probably what I have time for. I had another vignette about OOD generalization, which is another important subfield of AI alignment. But because I'm out of time, let me just leave you. I hope I've shown you that there are some nice mathematical questions here. I hope that some of you will want to get involved with this. Thanks. Questions?
Do you have a quantitative version of the integral over sigma x when you have like a function of like depth and the number of bits?
So I mean, I would guess that this continues to hold for higher depth, but we weren't able to prove that. Okay. But by the way, the proof, like the thing that you do is you decompose your activation function as a linear combination of Hermite polynomials, right? And then that makes everything simpler. Okay. But then as the depth gets larger and larger, then you start losing control over what's going on. But I mean, typical neural nets where like they're somewhat deep, but they're not that deep, right? I think yeah. Mm-hmm.
Think of methods like SHAP for interpretability.
Like what?
SHAP.
Sorry.
SHAP. Interpretability method.
Sorry, I don't know it.
Okay.
Yeah.
Wondering what you think the practical utility of these more theoretical approaches will be on this.
Yeah. So like in some sense, like a watermarking was an extremely special case, right? Where there was a theoretical question, and then it led directly to some code that we could implement, and it worked in practice well enough for Sam Altman to decide to not deploy it. Okay. Most of the kinds of questions that we're thinking about, I don't feel like even if we like solve some problem, like it probably won't lead directly to something to do right now, right? But the idea is like we are building these entities, that are soon going to be more powerful than we are across a huge variety of domains. And it's not just that we don't know the details of like how to align those things with human values, it's that we're sort of missing the basic theory. Right? Like almost everyone in this field would agree that we are sort of lacking the basic theoretical principles here. So, I am going to teach for the first time this coming fall a course at UT Austin on AI alignment. I'm still trying to figure out what the syllabus will be. Okay, because quantum computing, I know exactly what's the we have the Nielsen and Chuang textbook, right? It just we basic results that we've all agreed are foundational since the 1990s. Okay, the way that we were discussing this last night, we were saying there is no Nielsen and Chuang textbook for AI alignment. Right? There are no, sort of non-trivial results that everyone agrees are true and important. Okay, and so there is sort of a body of theory that does not yet exist, that will need to exist, in order to have a serious hope of doing this. Now, is there enough time for that to happen? Well, if the progress in AI were a little bit slower, I would feel better about that. Yeah.
If someone asked if there's a polytime algorithm to distinguish, or to say what's the probability that a random Turing machine of a fixed size would have this behavior, you'd say no, probably, like busy.
Probably, yeah. It's funny that you should ask that, because one of the questions, so we do collaborate frequently with ARC. They feed us questions. One of the questions that they fed us just a few months ago was literally about random Turing machines. Right, that
rule out this ever being applied to when you add in recurrence. If you have then it makes sense, maybe. But
yeah, no, I'm not sure. I mean, a random circuit like actually is a reasonable model for what a neural net is doing. Like each time that you run it, right? A random Turing machine would be another reasonable model that you could study. But I think there is some hope that you could do interpretability for, let's say, typical random Turing machine. So not in the worst case, not for all of them. That's going to be, well, I mean, if there was no bound on running time, then we're up against the halting problem and so forth. In practice, there is a bound on running time, which means that we are merely up against an NP-hard problem, let's say. Okay, but that's in the worst case, right? We care about the typical case. And again, we face an issue which is actually very common in theoretical computer science, which is that, the worst case is hard. We know that it's hard, but we also know that that's not the thing that matters in practice, right? The thing that matters in practice is much, much harder to characterize, right? So, like modern AI has worked as well as it did, even in the teeth of the problem of, let's say, minimizing the loss of a neural net being NP-hard in the worst case, right? People just go ahead and they train their neural nets anyway, and they find approximate solutions that are good enough, to give us ChatGPT and all these other wondrous artifacts. Okay, but you know, the trouble is like clearly, you know, gradient descent, you know, as actually run in practice, is exploiting regularities in real world data that didn't have to be there in the worst case, right? Like they wouldn't have been there if our training data was encoded a cryptographic pseudo-random function, for example. Okay, but it didn't, right? Because there were these regularities, you know, it was able to exploit them. But we have a really, really hard time as theorists characterizing what those regularities are, right? Why do these algorithms work in the typical case? Okay, but you know, often the best that we can do as theorists is to say, can we at least understand the random case, right? Can we at least say that, you know, this would have worked in the random case as a sort of stand-in for the typical case? Yeah.
What happened to Elias and the people who hired you? Do they still continue the alignment work, just not in?
So Ilya, after he, I only spoke to him once after he left OpenAI. That was when he was still figuring out what to do. After that, he announced a new company that he founded, which is called Safe Superintelligence Incorporated, SSI. Okay, they have explicitly said they will have no products and they will tell no one what they are doing. They have raised at least $32 billion. Okay? That is what you can do if you are Ilya Sutskever. Okay? So, you know, so indeed, I don't know what they're doing. Okay? They have been, you know, they are not telling anyone. Yeah.
About pseudo-random error correcting course there are for watermarking.
Yeah, so that was exactly what my former student, Sam Gunn, and his collaborators, Krist and Zamir, came up with in order to find like the real mathematical object that is sort of underlying, you know, watermarking schemes, sort of, you know, like the one that I showed, if you want real cryptographic indistinguishability, right? And that is how they were able to get that with these objects that they call pseudo-random codes. And now that, you know, and then they just started studying these pseudo-random codes in their own right because, you know, they were very interesting to them as cryptographers. And so now they have a whole sequence of papers about those. Now, you know, those watermarking schemes, like they give you the cryptographic indistinguishability, but, you know, but again, you know, I think the sticking point is robustness, right? They still don't solve the problem of the student who does that pineapple attack, right? Or the student who, you know, has GPT write their paper in French and then puts it into Google Translate. Okay, they can get robustness against like limited, like defined in advance classes of transformations. But, you know, if you have a user who can just do some arbitrary transformation, right, where they're just using GPT to help them, and then they're changing what it gives in an arbitrary way, then we're sort of lacking a basic theory for you know, what is even the definition of success there. Yeah.
Actually, just a question about that last point.
Yeah.
I mean, something that you probably don't want to watermark is a student who actually learns the material from talking with ChatGPT.
That's right.
And just writes it themselves.
Absolutely, absolutely, yeah. If a student just interacts with GPT and then they, you know, they learn something, they write it themselves, that seems great, right? That seems only to be encouraged. Now, fortunately, you know, none of the watermarking schemes that I'm talking about, like would typically, you know, induce a watermark in those cases. But that might be a thing to worry about for the future. Right? Maybe, you know, we'll all just start talking more like our LLMs if we spend enough time with them, and then all these watermark detectors will just start pinging all these false positives from us. Yeah.
You said something like, you know, LLMs are going to have this huge, or AI is going to have this huge impact in the near future, but you can't explain why. I take that to mean, you know, there's a poor understanding of why they actually work.
Yeah.
So what makes you so confident then that, you know, we're going to make rapid continued progress and that we're not just going to hit diminishing returns?
Right. So okay. So I'm not confident of that, but I'm also not confident that we won't. Right. And it's kind of like, you know, in other contexts, right? If like someone said, look, I don't know if there's going to be a nuclear war this year, but there's a 20% chance. Right, we would all understand that that's more than enough reason to be extremely worried, right? And here's like in the context of AI, somehow people have gotten the idea that if there's uncertainty, then that means that we don't have to worry, right? I think that that's not valid. Okay, so of course, scaling of AI might soon hit a wall. It might be that, the limit of what, any language model can do is precisely GPT 5.5 Pro, right? And, but, if I just do the naive thing of extrapolate over the last 5 years, I look at GPT-2, GPT-3, I look at, they were struggling with basic arithmetic problems, right? They were just, going off on random tangents, spouting nonsense. And you had all the skeptics of AI, like, Gary Marcus, Emily Bender, and so forth, pointing at these things and laughing, right? I'm saying, these are stochastic parrots. These are just next token, statistical toys, or there's obviously no real intelligence here. These are not useful. These are not good for anything. Okay, now, they are writing research papers. Okay, I regularly use GPT when I have a lemma that I need proven, right? And it can often prove the lemma much faster than I could. Hey, all like the entire nature of programming has completely changed, right? I remember years ago explaining to my daughter, as when I was teaching her programming, that programming does not just mean you say what you want in English. It is this, this whole thing you have to learn, this very precise language. Okay, and now here we are, and now that is what programming is. Okay, it is you just say what you want in English, right? And so we've seen that, the people who said this was hitting a wall, like every previous time, they were wrong, right? And it just kept accelerating, right? And the people who just extrapolated the trend on a straight line, those are the people who were right. Okay, and so I'm a strong believer in, like, and I was wrong about this, right? I didn't, I actually had dinner with Dario Amodei a decade ago, and he was saying, just extrapolate the straight line. We're going to have AGI in 10 years. The world will be a completely transformed place. And I said, you're full of crap. Okay, so I actually bet him $1,000 about it. Okay, and now, I'm planning to concede that bet. Okay, so the straight line extrapolators were the ones who were right so far. I'm a strong believer in when reality tells you something, you don't invent a convoluted reason why you were right all along. You just admit that you were wrong. And so that's what I've tried to do in this case. Yeah.
NP problems, making it safe. Mm-hmm. Use the good, like, let's say have good inputs. Don't they make it like bad outputs?
Sorry. So what would make it have bad outputs?
So if I have these NP hard inputs, right?
Yeah.
They give a bad output, and we're trying to make it safe, right?
Yes.
So, but
I don't know what you mean by an NP hard input.
Like the ones that result in kill-off.
Oh yeah, no, that's not the thing that is NP hard is the problem of deciding whether there is such an input.
Okay.
Yeah. Okay. Yeah.
More questions?